Hey, it's Doc Williams, and in this video, we're going to use the mole map to do particle to moles conversions. In this problem, we're asked how many grams of potassium phosphate is needed to react with 8.24 times 10 to the 25th molecules of aluminum nitrate. We want to identify our known and our unknown. For our known, we have 8.24 times 10 to the 25th molecules of aluminum nitrate. Our unknown, we want to know how many grams of potassium phosphate is needed to react. And to start our problem, we're always going to begin with what we're given, which is our known of 8.24 times 10 to the 25th molecules of aluminum nitrate. I am going to write molecules underneath just so that I have enough room to work out the problem. And since I have molecules, I'm going to begin where it says particles. Anytime I have particles, molecules, or atoms, this is where I want to begin, and I'm going to use Avogadro's number. Another thing to keep in mind is that whenever you begin with something other than moles, you want to convert that unit into moles. So since I'm beginning with molecules, the only place I have to go looking at the mole map is toward moles. And then going toward moles, I am going to use this conversion factor with 1 mole at the top and Avogadro's number at the bottom. To set this up, I will have 1 mole at the top, and that's 1 mole of aluminum nitrate, which would contain 6.02 times 10 to the 23rd molecules. Now I'm using molecules instead of particles only to match up my units, but it's going to mean the same thing. And this is going to allow me to cancel out molecules of aluminum nitrate and leave moles of aluminum nitrate. And now that I'm in moles, I will use the mole ratio to convert from substance A, which is aluminum nitrate, to substance B, potassium phosphate. And in order to do that, I will use mole ratio. So to set this up, I want to put what I want to get rid of at the bottom, which is moles of aluminum nitrate. And what I want to keep will be at the top, which is moles of potassium phosphate. I will use the chemical equation to grab the numbers that I will attach to my moles for potassium phosphate. Using the coefficients, when there's nothing there, we understand that to be 1. And for aluminum nitrate, we do not see a coefficient in front, so that is understood to be 1 as well. This will allow me to cancel out moles of aluminum nitrate, leaving moles of potassium phosphate. Now that I have used mole ratio to switch the substances from aluminum nitrate to potassium phosphate, I want to change from moles of potassium phosphate to grams of potassium phosphate. So going back to my molar map, in order to go from moles to mass, I need to use the mole mass ratio. And the one that's next to the arrow pointing from moles to mass is going to be the mass over moles. So to set this up, I am going to have 1 mole of potassium phosphate at the bottom and grams of potassium phosphate at the top. To calculate the molar mass, I will use the masses from the periodic table. I'm going to make a tally of each of the type of atoms that I have in potassium phosphate, as well as count each atom. So I have 3 atoms of potassium, and looking at the periodic table, that will be multiplied by their individual masses of 39.098 to give a total mass of 117.294 grams per mole of potassium in potassium phosphate. For phosphorus, I have 1 phosphorus times 30.974, looking at my periodic table. So that gives me a total mass of phosphorus in potassium phosphate of 30.974 grams per mole. We have 4 oxygens times individual masses of 15.999 according to the periodic table. Multiply that, which gives a mass of 63.6 0.996 grams per mole. Adding all of this up will give us the total molar mass for potassium nitrate to be 212.264 grams per mole. Now, my number is always attached to the grams component of the molar mass. So I will write my 212.264 at the top, and that will allow me to cancel out moles of potassium phosphate, leaving grams of potassium phosphate. So to do the math, I will multiply everything across the top in my numerators, take that answer and divide it by everything in the denominators, which gives 29054 grams of potassium phosphate. And since we only have two significant figures, we're going to need to round this to two sig figs. The numbers in our conversion factors will not count toward our significant figures. They are considered infinite numbers. While they are important, they do not count toward our measurements, which are our sig figs. So to write this number to the correct sig figs, I'm going to use scientific notation, which will be 2.91 times 10 to the 4 grams of potassium phosphate. So in our next problem, we're asked how many particles of aluminum phosphate is produced if 58.8 grams of aluminum nitrate was consumed. And this is going to be assuming that potassium phosphate is in excess. So the first thing we do is determine our knowns and our unknowns. Our known is 58.8 grams of aluminum nitrate, and we are asked to calculate the number of particles of aluminum phosphate. Beginning with what is given, 58.8 grams of aluminum nitrate. We are beginning with mass, and anytime we're giving anything other than moles, we need to go toward moles. So that will give us this conversion factor to use. We will set this up with moles at the top. 1 mole of aluminum nitrate. And we need to determine the grams of aluminum nitrate in 1 mole. To do that, we will calculate the molar mass using the periodic table. I'm going to make a tally of each type of atom that I have in aluminum nitrate. I have 1 atom of aluminum, and looking at the periodic table, it has a mass of 26.982, which will give me a total mass of aluminum in aluminum nitrate of 26.982. For my nitrogen and oxygen, I am going to multiply each of these elements inside the parentheses by the number that is outside the parentheses. Basically, it's just like the distributive property in math. You're going to multiply everything inside of the parentheses by what is outside. And where nitrogen has no subscript behind it, we understand that to be 1. So 3 times 1 would be 3 nitrogens. And 3 times 3, which is the subscript behind the oxygen, would give us 9 oxygens. Now, nitrogen has a mass based on our periodic table of 14.007, which gives a total mass for nitrogen of 42.021 grams. And oxygen has a mass of 15.999 on the periodic table, which gives a total mass of 143 0.991. To find our molar mass for 1 molecule of aluminum nitrate, we will add all of these together, and the molar mass will be 202.994 grams per mole. We always attach the number to the grams, so grams will be at the bottom, 212.994. And this will allow the canceling out of grams of aluminum nitrate and leaving moles of aluminum nitrate. Now that we're in moles, we want to convert from one type of substance to the other type of substance using mole ratio. And to do that, we're going to need to go to our chemical equation. So let's set up our mole ratio. We want to cancel out moles of aluminum nitrate. So whatever we want to get rid of, we put at the bottom. And we want to keep moles of aluminum phosphate, so we're going to put that at the top. To grab our numbers, we're going to go to the chemical equation and look at our coefficients. So for aluminum phosphate, we do not see a coefficient, and that's understood to be 1. And for aluminum nitrate, we do not see a coefficient, and that is also understood to be 1. This will allow us to cancel out moles of aluminum nitrate, leaving moles of aluminum phosphate. So now that we're in moles of aluminum phosphate, we want to go to particles for aluminum phosphate. And looking at our mole map, we're moving from moles to particles. And this gives us the setup of the conversion factor that we would use. We would use Avogadro's number with particles at the top and moles at the bottom. So 1 mole of aluminum phosphate at the bottom and 6.02 times 10 to the 23rd, Avogadro's number of particles of aluminum phosphate at the top. I'm just going to put a P here to abbreviate because I don't have any more room. This will allow us to cancel out moles of aluminum phosphate, leaving particles of aluminum phosphate. Now we do our math, which will basically be multiplying 58.8 times 6.02 times 10 to the 23rd, since everything else is 1, and dividing it by 212.994, since everything else at the bottom is 1, which will give us 1.66 times 10 to the 23rd particles of aluminum phosphate. And I wrote 1.66 because we have 3 significant figures. As always, thank you for watching.